So how does a solar photovoltaic cell work, and how good can they be? So basically you put the cell somewhere where it's exposed to the sun, sunlight comes in, it causes electrons to flow out one side and holes to flow out the other side, and that's run through a load, typically an inverter, and powers things. Now basically the solar cells are just very big diodes. So a diode is like a one-way valve for electricity. It allows current through one direction, not the other. And solar cells are diodes designed to let light in. Now the way diodes work, like many semiconductors, is you have doped silicon. And semiconductors like silicon, when they're doped, they have two energy levels. There's the valence band, which is normally full of electrons, and a conduction band. And if an electron is knocked from the valence band into the conduction band, it can then move around. It also leaves a hole behind, which can also move around. Now normally, you dope these things to produce p-type and n-type regions, which is the one-way valve. Normally, electron can't get from one side to the other. So that would be just a normal diode. However, what happens now is that when light hits the cell, it'll knock an electron from the valence band into the conduction band. Once in the conduction band, it'll flow down the potential difference and out one side, giving this amount of usable voltage. And then the hole will go out the other side, or equivalently be replaced by an electron moving in from the other side, and that's what supplies the power. So basically what you've got is a piece of silicon, the band gap between the valence and conduction band, and light knocking electrons from one to the other, and then the doping causes them to flow around and produce the power. Now this process is what limits the efficiency of solar cells. We said a typical commercial solar cell is maybe 20-25% efficient, and here's the major reason why solar cells can't be 100% efficient. We've talked about efficiency before, the Carnot limit in thermodynamics. This is not a heat engine, so there's no Carnot limit effect here. The limit mostly comes from the energy of the photons arriving. Now this diagram is a spectrum of the sun. This is showing you how much emission the sun emits at every different wavelength. And the red line is what the sun actually emits as you'd see it from space. And the green or blue lines are what actually gets through to the Earth's surface. And as we talked about before in the global warming section, we can see there are dips due to absorption of different molecules, mostly water vapor, in the Earth's atmosphere. So the green or blue lines are what gets through depending on the angle in the sky and the exact weather conditions at the time. Now the trouble is that the band gap energy of silicon corresponds to photons with a wavelength of 1.1 microns, 1100 nanometers. Now remember that the energy of a photon is h nu, h Planck's constant times its frequency, which is h c on lambda, c the speed of light, divided by the wavelength. So the shorter the wavelength of a photon, the more energy it has. So the photons down here, the ultraviolet ones, have a lot of energy. Each photon packs a big punch. X-rays or gamma rays will carry even more, but the sun doesn't emit very many of them. Whereas the photons out here at infrared wavelengths are very pathetic and don't have much energy. Now, for a photon to knock an electron from the valence band into the conduction band, it has to have this amount of energy. If it has less than that, because it's quantum mechanics, things can't go part way. They either have to get there or not try anything. They're not going to jump part of the way. What that means is that any photon on the right-hand side of this diagram does not have enough energy to knock an electron up between the two levels, and so it basically will not produce any power. So all the energy of all these photons down here, your solar cell does not pick them up. In fact, at these wavelengths, the solar cells are almost completely transparent. The light just goes straight through and out the other side. So that immediately tells you that you've lost a substantial amount of power, because all the infrared light from the sun, anything beyond 1.1 microns, a solar cell built of silicon cannot pick it up. I call it a detector because exactly the same thing applies to the astronomical detectors we use. This is the same reason why we can only see certain wavelengths with certain detectors. And I spend a lot of my time looking at detectors and how they can analyze things in space. So all these long wavelengths, sorry, throw them away, can't get them. How about these? All these photons up this side do have enough energy to knock an electron up to the conduction band. The trouble is that some of them have too much energy. So something here has just enough energy to knock the photon from there to there, whereas something down here is at a shorter wavelength, so it's got more energy. So what that's going to do is, instead of knocking it from here to here, it might knock it from here all the way up here somewhere. Is that a problem? Well, no. Things can be knocked up. They can be knocked from here up to there, and then they can release that energy by causing lattice vibrations or lattice thermalization, i.e. heating up the solar cell. So that's not a problem. You still produced an electron, but you've wasted some of the energy. So a photon here, you can get 100% of its energy into energy of the electrons, but something down here might have 3 times more energy for photons, so only 1/3 is actually going into useful electricity, and the rest is going into heating up your solar cell. So what this means is, if the sun just emitted all its energy just around this wavelength, just below the bandgap energy of silicon, then you could have solar cells that were nearly 100% efficient. But because the energy is spread out, you lose everything to this side, and this side you get only the 1.1 micron energy. Anything above and beyond it is wasted. That's one loss mechanism. There are actually numerous other ones. You'll lose some voltage at the junctions and contacts, and there's recombination. Some of the electrons will jump down all by themselves rather than flowing through the diode, and some of the light will bounce off the surface and be reflected rather than be properly absorbed. But this is called the shock equalizer limit. This is the limit purely due to the fact that some wavelengths are wasted and other wavelengths give too much energy, and that means that any solar cell made of silicon can never achieve more than about 30% efficiency. That's just the nature of silicon with its bandgap energy and the spectrum of the sun. And current commercial cells are pretty close to that. They're about 24% efficient, so all the other forms of loss have been removed pretty much, and you're getting pretty close to your theoretical limit. Can we do better than this? Well, there is a lot of research. You can maybe push that 24% up a bit closer to 30%. But if you want to go above that, you're going to have to use something other than silicon. Any other semiconductor will also have a bandgap energy at a particular place, and so will have wastes at both sides. So there's a bit of a trade-off there. What some people are looking at is having multiple layers. Particularly, you might have a layer of perovskite, which has a higher bandgap energy, and that can mop up the ultraviolet and blue photons. And then anything that gets through that will then be mopped up by a silicon layer underneath, which is better at picking up the red and infrared photons. So having multiple layers can give you efficiencies up to 40% at the expense of much more complicated solar cells.